inequalities are compatible with the unit interval integration region. So we still have n minus 3 integrations to perform over some hypercube, strict ordering. And in the foreground example, which we took as a introductory one, there's only one integral over the second position to perform, and it was just a choice of convenience to do it for particle 2, not for any other one. And as another matter of convenience, the integrations which are dropped, I mean the corresponding functions, can be set to any real number, and this is related to the desire to have the unit interval here. So another matter of convenience, we set this triplet of fixed functions to 0 from infinity. Okay, so this is the general description. You have to evaluate the correlation function of various neural vertex operators using the big rule stated over there, and you'll certainly get integrand of the Covariance type. Then the leftover task is perform the integral over that guy along with various denominators like here. Let's look at some examples, starting with the almost trivial 3.1. The 3-point integral, the 3-point amplitude, you have no integration to perform at all. So let's start with this Jacobi determinant from the fixing of the 3 punctures. And let me write out the correlation function that determines the 3-point amplitude. You have the 3 external Luhmann polarizations, epsilon 1, epsilon 2, epsilon 3. And they contract into the conformal field IDX. So there are 3 of them, which call for the big rules from the network over there. Here the Covariance factor completely trivializes. The Covariance factor is simply unity in the 3-particle phase space, since the aspect sends all the Mandelstam invariants to 0. So that Covariance factor, which always factors out, is not visible here in this 3-point context. And instead, what we get is there are now 2 topologies of terms, how you can perform the contractions. Either you can choose to make one contraction among the x's. So if you go for this contraction here, you will build up a dot product epsilon 1 dot epsilon 2. And then the other one has no other choice than contracting with the exponentials. And from the exponentials, you'll get a dot product with external momentum. Really, there are 3 pairs of 3 x's which you can contract into each other. Okay, so this is one kind of contribution. But also, there is the second topology where all the dx's contract into the exponentials. That's a good way of drawing that. So independently, they contract into the exponentials. And that is 2 alpha prime very careless about the overall coefficients. I haven't tracked carefully the absolute powers of alpha prime, but what I would like to emphasize, there's a relative factor. There is one more alpha prime in the second class of terms as compared to the former ones. And from this you can see that there's really different physics in the two kinds of terms. Here, this orbit of E dot E contractions, this simply corresponds to the Yang-Mills interactions. Here we have just recovered the cubic vertex of Yang-Mills. And on top of that, as an alpha prime correction, this is an effective vertex which you can identify the cube of the gluon field. So, in summary, by going through this three-point calculation of the bosonic string, we have seen that there is a string-specific vertex type cube. Okay, let us now move on to the simplest non-trivial integration at the 4-point level. And no need to worry, we won't go through the full glory algebra of the 4-point correlator, but simply look at one particular tensor structure from which we can learn a lot about tachyon exchange. Okay, so it's the following. Let's go for a subset of the 4-point function computed with a prescription over there, where we only track the tensor structure where the polarization vectors contract to each other. This is a very small subset of terms. Okay, let's see. What does the prescription tell us to do at 4 points? As always, we fix 3 of the punctures to 0, 1, and infinity. Let's do this for 1, 3, and 4. According to that Lienian statement over there. And the integrand is, okay, again, I first take out the polarization vectors. Those terms where the tensor contractions goes like E1 dot E2, E3 dot E4. So I only look at the big contractions from here and from there, which produce the desired stuff. Remember, we will send one of the punctures to infinity, let's say Z4, and like that, a lot of terms will cancel each other, and also the Cauchy-Nielsen factor will become very slim. You might fear that there are altogether 6 pairs to consider, but in this level fixing 0, 1, and infinity, the Cauchy-Nielsen factor only has 2 terms, namely those guys. These are the ones which you saw in the introductory example. Okay, so taking all these considerations about the Z dependence into account, we are left with integral of over the unit interval, Z2 raised to the power of S12, and now what survives is here, this double denominator. whereas the 1 minus C2 is not receiving any further contributions. The exponent is a naked estimate. Okay, now let's look at this integral from the viewpoint of the whole expansion. If we do the same binomial expansion of the 1 minus C2 bracket, then what you get is an expansion of the type S12 plus n minus 1. Let's not care about the residues. Although this might sound a little bit pedantic, I should really emphasize the minus 2 has a huge impact about the spectrum of states exchanged. This offset of minus 2 leads to first pole at S12 equal to 1, which is followed by a massless pole and the tower of, say, resonance exchange poles. Okay, so clearly here we have a honest-to-God Feynman diagram for massless theory. Here we have a honest-to-God one exchange. And about those we have already talked before. These are the massive string states at positive mass squares. So by exclusion, all that this guy can be here, this is a pole of the opposite sign range of Sij. This must be a quite exotic state. This is a so-called tachyon at negative mass square. Okay. I mean, certainly we could have talked about the tachyon way beforehand when the vertex operators were introduced. Certainly the tachyon appears as a solution to the conformal invariance requirement. But I decided to go a slightly different way, to first jump at the gluon, since this is what we want, and now to see a posteriori. Even if we just had a gluons, we will be hit with our face onto the tachyon. So here from this particular regime of the 4-point function, we see that the tachyon insists to be inside the theory. And that's how it shows up. And I went through the calculation in big detail to, in the next step, convince you that the superstring is more convenient. First of all, in view of the hat-cube interaction, which won't be there. And secondly, in view of how the superstring will get rid of this elephant. So this is the preview of what I'll do now. Any questions on the bosonic string before we leave that topic? Alright, let's go to open string, please. And let me again start with the basics of the worldsheet function. Namely, we will need worldsheet supersymmetry as the foundation of the RNS superstring. Okay, what we will do is we will supersymmetrize the bosonic strings action by adjoining some spin-off bits, psi and psi bar. This is a doublet of worldsheet spinors, which enter on the following way. Okay, first of all, I copy the bosonic strings action. Nothing new on this front. But here on top of that, there's the fermionic thread. Where the two fermions, psi and psi bar, that with the buzzword worldsheet supersymmetry. Let me specify the invariants. Then simultaneously change the x fields by a variation proportional to size, and at the same time you should vary your fermions by the holomorphic and anti-holomorphic derivative of the x. This is just the symmetry algebra in 2 dimensions. Bosons go to fermions, fermions go to L bosons. Such a SUSY's anti-commutative. Oh yeah, there's one thing that deserves clarification. As I said, we are adding a spinner variable here. Psi is a spinner from the worldsheet perspective, but not so in space-time. From the space-time point of view, we are still having vector indices, which run from 0, 1, up to critical dimension. So certainly, psi bar are space-time indices. However, the statistics from the worldsheet point of view is binorial. And this is already a source of trouble. As a drawback of the RMS string, you only have worldsheet spinners, but you want to have space-time supersymmetry at the end of the day. So here this description is backing manifest space-time supersymmetry, and tomorrow I will offer a way out using the spinner. But since we won't go through fermion calculations explicitly, this won't ask too much. Okay, so here this is the invariance of the worldsheet action. Psi and dx are related by the supersymmetry. And now that I've introduced the new field, I should tell you how to compute its correlation functions. And once more, the essential information is sitting in the kinetic operator. Once you invert the kinetic operator of psi, you will find that the 2-point function at G0 goes like the Minkowski metric divided by C1 minus C2. Very good that we are having a simple pole. This means that the statistics is Rassmann what, or let's say if I anti-commute the two, the right-hand side flips the sign, this is expected. Okay, so this is the toolbox from which we will construct our tree amplitudes and the first step our vertex operators. And in fact, the vertex operators, they appear in a doublet. A doublet with respect to this worldsheet supersymmetry. There's not only one vertex, but in fact 2 of them. And to distinguish them, I add some new superscripts. One version of the superstring Gluon vertex will have this -1 superscript. And it is given by the J polarization vector contracted to the worldsheet spinner. And again, the old friend is. Okay, now to complete the worldsheet supersymmetry multiplet, I should give you a second version of the same state, namely vertex operator with a 0 superscript. We will also call these superscripts the super ghost picture. Okay, so here the second version is, first of all, recycling the bosonic string vertex operator. On top of that, there is some completion to it, which goes with 2 powers of the spin of psi. Pictures per state connected by worldsheet supersymmetry. So this looks a little bit inconvenient. More vertex operators than states we want to scatter, so I have to tell you how to choose the appropriate one in a given setting. So let's left the bosonic string behind, you won't see this EOS subscript anymore. So without specification here, we are doing the superstring. And I'll introduce in super YAML's subscript when necessary. Okay, unfortunately the bosonic string description is still there. We'll do more or less the same as here. We first of all start with this huge integral using 1, and let's for the moment pretend we only know the 0 picture. Let's just align some 0 picture vertices along the real axis. And the same way as we had to divide out by the conformal bosonic string, we will now have to divide out by the super conformal plus supersymmetry approach. So here, colloquially speaking, I'm dividing out the volume of the super SO2. Okay, let's fill this with a very concrete description, what to do. So, first of all, there is the conventional SO2R, and with this guy, I proceed as before. And as understood, I fix 3 punctures to anything I like. I choose the punctures 1 and minus 1n as before, and I evaluate the correlation function at 0. I've started from the 0 picture vertices. So this is, if you wish, the default vertex operator. In the same way as 3 bosonic degrees of freedom have to be fixed here, I now have to fix 2 fermionic degrees of freedom. So now I have to adjust the ghost pictures in such a way that 2 of them become minus 1. And let's say I choose number I and number j, vertices I and j, which go to the minus 1 picture. So 2 of these Q superscripts become minus 1 for L equal I equal j. Then I have to do some compensation. I have to divide by this corresponding propagator. In fact, this is propagator of some super ghost field of the world chip, which I am keeping out of this discussion for simplicity. But if you go through the full machinery of super ghosts, then you will first of all see the origin of this guy. And first of all, a crucial property, which is not fully obvious from the material of the blackboard, this expression is independent on the choice of I and j. You can approach me after the lecture if you want to have more details. Otherwise, just accept this as a very cool property of this superstring prescription. You're completely free to choose to fix your fermionic moduli any way you like. Put any of the any 2 gluons into the minus 1 picture, and your amplitude won't depend on that choice. Maybe this reminds you of Alice's lecture, and he told you that the Pfaffian has some null vectors, and that one has to erase some rows and columns from the Pfaffian. Choosing the I and the j to be the minus 1 picture is exactly equivalent to erasing rows and columns I and j from the Pfaffian. Okay, now we have seen how to compute the superstring tree amplitudes. Let's again go through some examples. 3.3, and the business starts as usual. This is from fixing three punctures. These are the dual polarization vectors that factor out from both choices of vertex operators. And now let's decide upon which vertices to put in the -1 picture. Let's do Z2 and Z3 in the -1 picture. So I start by writing down the 0 picture vertex from here. And the other two are just in the -1 picture. In other words, they're significantly shorter. So this is N, this is P. Okay. Again, the covariance factor won't cause any trouble because the some variables vanished here. And the result is independent of disease, as it should. So let's go through both sorts of terms. You can take the dx field from the 0 picture vertex, which will, as always, contract the exponentials. And like that, you produce the dot product E1.8. And now the second class of terms is when you have more psi's, namely double psi from the 0 picture vertex. This contribution will give you the red terms. If you assemble everything, the answer is cyclical invariant and reproduces the Young-Mills 3-point vertex, which you've already seen before. And most notably, there's no additional FQ vertex. So in that sense, the superstring is cleaner than this bosonic friend. And it's a nice consistency check in practical calculations. Suppose you're not sure about the plus-minus sign here, just check whether cyclic symmetry emerges, and then you can make sure that you have done all the algebra correctly. Good. This finishes the 3-point amplitude, and I think the 4-point amplitude will be the right portion to conclude. Let's discuss the tachyon-free 4-point amplitude.